Welcome to qnawire.
So we have two astronauts who are meeting in space for a secret meeting, and we're conveniently told to model these astronauts as two spheres, and then asked to draw a free body diagram of the situation. So here are two spheres. We have astronaut A and astronaut B. The only forces acting on them are the gravitational force of each astronaut on the other. So on astronaut A, we just have the force that astronaut B is applying to astronaut A. And on astronaut B, we have the force that astronaut A is applying on astronaut B. So we're then asked to find the acceleration that each astronaut will experience. So from Newton's third law, we know that those two accelerations are going to be the same, or rather the magnitude will be the same, the directions will be opposite. So to find that value, we say that the magnitude of acceleration A is equal to the magnitude of acceleration B. And because this is just a gravitational force, we know that will be the gravitational constant g times the masses of the two astronauts, and then divided by the distance separating them, RAB, and we're told that's 20 meters. So we also know the astronauts' masses, so we can just plug everything in here. So g is 6.67 times 10 to the negative 11th. And I'm going to leave the units out here and kind of trust that this is all going to give us newtons in the end. So then we have astronaut A's mass of 65 kilograms, astronaut B's mass of 72, and then their distance of 20 meters separating the two, so 20 squared on the denominator. And when we evaluate that, we get a force of 7.807 times 10 to the negative 10th newtons. So each astronaut applies the same force to each other, but because they have different masses, they'll experience different accelerations. So the acceleration that astronaut A experiences will be that force divided by the mass of astronaut A. And so plugging that in, 7.807 times 10 to the minus 10th, and then that mass of 65 kilograms, we get an acceleration of 1.2 times 10 to the negative 11th meters per second squared. And for astronaut B, FB over the mass of the astronaut, and again, FA and FB are the same here. Doing this, we'll get 1.1 times 10 to the negative 10th, or 11th, sorry, meters per second squared. So that's part A here. And now in part B, we're asked if we assume this acceleration stays constant the whole time, how long will it take for the two astronauts to meet? So these accelerations are going to change as time goes on. The astronauts get closer, but we're just going to say it's going to keep these constant values the whole time. So this becomes a basic kinematics problem then. And so probably the best way to do this is to use our kinematics equation for constant acceleration. So we know that x as a function of time for a given object is going to be the initial position of that object plus the initial velocity of that object times time plus 1/2 times the acceleration of that object times t squared. So we just want to write down an x of t equation for these two astronauts and then set their final positions equal to each other and solve for what time it'll be that happens at. So at this point, we have to kind of make some decisions about what we're going to call the positions of these two astronauts. So this is completely arbitrary. You can make any coordinate system you want here. As long as you're consistent, it'll work. But I'm going to call the position of astronaut A x equals 0, and the position of astronaut B x equals 20. So they're still 20 meters apart. I'm just saying that A is the one that is at position 0. So then for astronaut A, there's no initial velocity, there's no initial position. So its position as a function of time is just 1/2 its acceleration, so the acceleration of astronaut A times time squared. And astronaut B is going to be an initial position of 20 plus no initial velocity, and then plus 1/2 B acceleration times t squared. And then actually, because these two astronauts are moving in opposite directions, if we've called astronaut A is moving in the positive direction, really that means then astronaut B should be moving in the negative direction, so it has a negative acceleration. So now we just set xa equal to xb. We want to know the time that they have the same position, and then we'll solve for the time. So 1/2 acceleration of A times t squared equals 20, and then minus 1/2 times the acceleration of astronaut B times t squared. So the only unknown in this equation is time, so we just solve for time here, and we should get that that is equal to the square root of 2 times 20 meters divided by acceleration of astronaut A plus the acceleration of astronaut B. So those two values that we found in part A. And so we can evaluate that, and we should get 1.32 times 10 to the 6 seconds. And I think actually they ask us for the number of days, and that's also probably a more useful measure here. So if we convert that to days, we get that it's about 15 days here. And then for part C, they ask us what would happen as the two astronauts actually get closer to each other. Well, just looking at our equation here for the force, we see that there is a dependence on the distance between the two astronauts in the denominator. So the smaller the distance between them, the stronger the gravitational force will be. So as they get closer to each other, these accelerations are going to increase. So this will end up taking somewhat less than 15 days, but still this is probably not going to be the best way for them to plan a meetup of just relying on the gravitational force.